In this example, we're going to look at a specific application problem that's a quadratic function, and we're going to use the key characteristics of a graph to sketch a graph and also to answer important questions about this particular problem. Let's start by looking at the situation. We have an arrow shot straight up into the air, and this is our function h of t equals negative 16t squared plus 90t plus 6. Gives the height in feet of an arrow after t seconds. Round answers to 2 decimal places as needed, and all answers must include appropriate units of measure. The first question that we're asked to do here is to sketch a graph representing the height of the arrow over time. Being able to look at and visualize what's happening in the graph is very important and very helpful in interpreting the solutions to a complex question like this. One thing that I think it's important to notice here is notice that we have a function and our variables are a little bit different than what we usually use when we're talking about sketching graphs. If we think of our function notation, what this means is our function is h, and that's the height, and our input variable is the t, which is the time. So if we think in terms of inputs and outputs, our input variable is t, and our output variable is h, which is what's coming out, or h of t, and that's what we get when we evaluate the function. Input variables traditionally relate to x, and output variables traditionally relate to y. So if we can use this type of thinking over here as we sketch the graph and put some labels in, it's really going to make some of this interpretation a lot easier. This is normally the x-axis, so in our case this is going to be t, which is the time measured in seconds. This up here is the y-axis, and in our case that means that we're looking at the height, which is the height, and that was being measured in feet. So those are going to be the axis labels and the variable pieces that we're going to be using as we go through and talk about our input and output in figuring out these key characteristics. Other than that, let's go ahead then and take a look at our key function here. The first thing that I'd like you to notice is that the a value, if we go through, we often like to look at the a value, the b value, and the c value, so these coefficients give us some important pieces of information. In this case, our a value is negative, which means that our parabola is going to be opening down. And it will have this type of a shape. And that kind of makes sense if you think of an arrow is going up in the air and then coming back down. So that having that upside down as piece is going to be an important part there. And that's because our a value is negative. So a was less than 0. This highest point of the graph is always a very important point, so we'd like to actually go ahead and calculate what that vertex is. The vertex we find by using the formula x equals negative b over 2a. In our case, our b value was 90, so we're going to have negative 90 on top, and our a value was negative 16, so we're going to have negative 90 divided by negative 32 on the bottom, and we can evaluate what that is in our calculator. So let's see, negative 90 divided by negative 32 gives us 2.8125. The problem said to round to 2 digits after the decimal, so we'll go ahead and use that as the x-coordinate of our vertex. The y-coordinate of our vertex we get simply by putting that 2.81 into our formula. So if we replace all of the t's with 2.81, we're going to have negative 16 times 2.81 squared plus 90 times 2.81 plus 6. All right, let's go and evaluate that. Again, let's clear out this. We're going to have negative 16 times 2.81 squared plus 90 times 2.81 plus 6. Gives me 132.56. So my vertex is going to be located at the point 2.81, 132.56. Let's go ahead and plot our vertex over here on the graph. Because our vertex is at 2.81, just counting by ones on the x-axis is probably fine. So we have 1, 2, 3, 4, 5, 6. 2.81, we're right about here. That's going to be our axis of symmetry because that's where our vertex is located. The height, however, is up at 132.56. That's pretty far up on the axis. So maybe count by 20s. 20, 40, 60, 80, 100, 120, 140. So we're going to be out about halfway there. So that's going to be the point of our vertex. And I'm going to go ahead and just write the coordinate point here as reference for us later. 2.81, comma, 132.56. All right, so that's a really key important point. Now remember, I'm going to be looking at a parabola that's going to be going downhill like this, upside down parabola, because we have that negative in front of the t-squared. So how do we find some other points? Well, the easy ones to find are the vertical and the horizontal intercepts. And they actually often have some really important meanings that we will want to look at anyway. Not the vertex, but the vertical intercept we'll do first. In order to find the vertical intercept, what we want to do is we need to set our input to 0. And when we put that in, so we're going to put in 0 for t. So we're going to have h of 0 is equal to negative 16 times 0 squared plus 90 times 0 plus 6. And that comes out to just be 6. So the vertical intercept is located at the point 0, 6. These were counting by 20s, so 0, 6 is right about there. So remember, this is 20, 40, and so on. This is 1, 2, 3, and so on. All right, so there's our vertical intercept. It's going to be coming down this way, and then it'll probably clip really close here for a horizontal intercept, but let's go ahead and calculate it. To find the horizontal intercept, we want to set the output equal to 0, which is a little bit different. So here we're going to find 0 equals negative 16t squared plus 90t plus 6, and we want to solve this equation. Because we have a t squared and a t in it, we're going to have to go ahead and either factor or use the quadratic formula. I'm going to trust that that doesn't factor nice, and let's go ahead and dive into using the quadratic formula here. In this case, x equals are really our t equals, right? Because we're thinking of both of those as our input variables. It's going to be, our formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Plugging our numbers in. Remember, our b was 90, so we're going to have negative 90 plus or minus the square root of 90 squared minus 4 times our a was negative 16, our c was 6, and we're going to divide the whole thing by 2 times negative 16. Let's go ahead and simplify that down just a smidge and see if we can get something that is a little bit easier to work with. We'll pull up our calculator. Inside the square root, we're going to have 90 squared minus 4 times negative 16 times 6. That's 84. So we're going to have negative 90 plus or minus the square root of 8,484 divided by negative 32. And then if we pull our calculator up, we can go ahead and come up with our two solutions. If we use the plus in our symbol, what we want to do is do negative 90 plus the square root of 8,484. And then we want to divide that answer by negative 32. That gives me negative 0.07 as one possible horizontal intercept. If we look at, so negative 0.07 comma 0. So that kind of makes sense here. If you look at our picture, it's going to be coming down real close like this, and it's just barely going to be over there on the negative side. To get the other solution, we're going to use the subtraction in our expression from the quadratic formula. So here we're going to have negative 90 minus the square root of 8,864. I'm sorry, 8,484. Try that again. And then we want to divide that answer by negative 32. In this case, that gives us 5.69 when we round to 2 digits. So my other horizontal intercept is located at 5.69 comma 0. And that will come down here. That's 3, 4, 5, 6. 5.69 is going to be about halfway. and it'll come down this way for my parabola. So this is a nice general shape of my parabola. I've got a couple of horizontal intercepts here of interest. I've got a vertical intercept, and I've got a vertex. And a pretty nice sketch to see what's going on. We can see the arrow gets shot in the air and then comes back down again. All right, so let's use this information then to go ahead and answer the different questions in the problem. The first question asks, how long does it take for the arrow to reach its maximum height? Well, anytime it talks about a maximum, what we're looking at here when we're looking at a parabola relationship is the vertex that goes on. So if you follow the track of our parabola here, the height is going up, up, up till we get to here, and then it's coming back down again. The first question here is asking how long. That's a question about time. So we want to know what is the time that it takes for the arrow to reach the maximum height. That's going to be the input coordinate of my vertex. So in this case, at 2.81 seconds, my arrow is going to reach its maximum height. If we're being asked, next we're asked to actually determine what that maximum height of the arrow actually is. Well, this is going to be the y-coordinate of the vertex, because remember, if we're looking here, the y-axis measured the height, where the x variable or input variable measured the time in seconds. So the maximum height is also, again, talking about the vertex. Here we were asking for how long, so we wanted the time or the input. Here, spell that right, input. Here we're asking for the actual height, so we want the output in feet. Looking at our coordinates, we did all of that solving earlier, which is great because now we have the information we need and we can just answer the question. The maximum height of the arrow happens at 132.56 feet. All right, well, let's see what other questions we can answer by looking at our graph and our formula. The next question asks, how long does it take for the arrow to hit the ground? Well, if we're looking at our picture again up here, notice it goes up, 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 and then it comes down, 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 down. And where it hits the ground is right here at height 0. So we want to know the time when it hits the ground. In this case, what that is really asking us for is what's the horizontal intercept. So if we look over here, our horizontal intercept calculations, that's going to happen at 5.69 seconds. Now notice there is another horizontal intercept over here, but the time is negative, which really doesn't make any sense. Nothing really happened from a practical perspective before we started firing the arrow. So even though there was another horizontal intercept there, we're going to go ahead and ignore it because it's not a practical solution to the question that they're asking us in this problem, even though it's part of what the graph looks like. The next question asks us to identify the vertical intercept, to write it as an ordered pair and interpret its meaning. We found the vertical intercept over here and notice that it happens at the point 0.06. And again, the vertical intercept is where it's crossing the y-axis, and that's right there at that point. So our vertical intercept is at 0.06. The next piece asks us to interpret its meaning. Remember that the x-coordinate was measuring our time in seconds, and our y-coordinate was measuring our height in feet. So that's the pieces of information that are really helpful. So what this means is when we shoot the arrow at time equals 0 is actually when we shoot the arrow. So when we shoot the arrow, the height we shot from was 6 feet. It's probably the height of whoever the shooter is, and that should make sense. I don't know if any of you ever tried to shoot an arrow while lying on the ground. It does not really work very well. So in terms of an interpretation, talking about at time 0 when we shoot the arrow, the height that we were shooting from was 6 feet. So that's one way that you can talk about it. All right, so you can see that each of these pieces of information that we found, the vertical intercepts, the horizontal intercepts, the vertices or the vertex, all give us important information that are relevant to an interesting interpretation of the actual graph. The last piece of the problem here asks us to determine the practical domain of h of t and the practical, this should be the practical range of h of t. Don't need to answer the same question twice. So usually we talk about domains and ranges. Normally, if we were looking at the range and domain and range, usually for quadratic functions, the domain is all real numbers, and then the range, in this case, for example, would be all heights less than 132.56 feet because that was the maximum value. Well, if we're talking about practical things, once the arrow hits the ground, it's not going to keep traveling. So anything where we have a negative y value is not going to make any sense at all. Similarly, before we shoot the arrow, we don't have any measurements and nothing is happening. So even though our parabola does extend over here into the negative x-axis, it doesn't give us any useful information. So this is the idea of what they're talking about when they talk about a practical domain and a practical range. For us, the practical domain or practical values of x are going to be when we shoot the arrow. So starting at t equals 0, I don't care about anything before that. And then I only care about till the arrow hits the ground, because after that nothing interesting is happening anymore because it's on the ground. It hits the ground here when the height is equal to 0, and that happens at 5.69 seconds. So we can talk about the practical domain of h of t as being all values of t in between 0 as the lowest value and 5.69 as the highest value. And each of these would be, of course, in seconds. So all the times between 0 seconds and 5.69 seconds. The practical range is going to be the different values of height that we could take on. The lowest height that we ever get to is when the arrow crashes into the ground, and that happens at h of t. That happens when it's 0. The highest value that our arrow traveling can take on is the vertex up here at the top, and that happens at 132.56 feet. So that's going to be the extent of the practical range. I only really care about the heights between 0 and 132.56. And for the time, I really only care about from when I shoot the arrow until it falls onto the ground. So those become the practical domain and the range for our function, even though the actual function could be defined for greater periods of time. Anyway, hope that helps, and we'll look at some more applications in class.